Okay, first let's talk about what acceleration actually means. So acceleration is the rate of change of velocity. In other words, speeding up, slowing down. If something's speeding up, it's accelerating. If something's slowing down, it's decelerating, or it's got a negative acceleration. Okay, you can calculate acceleration using this equation. Acceleration is change in velocity divided by time. Okay, so this delta, this little triangle here, that's delta. That's the Greek letter delta. That's change in. We use it to say change in velocity divided by time. So this whole experiment really is actually way simpler than it seems. So you've got a car that's being accelerated down the track. Okay, now in order for the car to accelerate, it needs to experience a resultant force. It needs to experience a force that's going to pull it along the track and cause it to get faster. And it does that, we do that, by having these slotted masses at the end. You saw the slotted masses at the end. It's going to have a force of weight acting downwards, which will cause the car to accelerate. That force of weight will be transferred along this string, and it will pull the car along. Okay, there's the force F. That's going to cause the car to accelerate down the track. Okay. Now, all we did was we changed this the size of this weight, the magnitude of weight by we changed the amount of masses on this hanger at the end here. We changed the amount of masses. Now, notice as well, if you remember from the video, we took the masses off the top of the car. The reason being was the whole point in the first experiment was to hold mass constant. Now that's the mass of the whole system. Okay, think about what's being accelerated here. The car is being accelerated because it's experiencing a force, so it's being accelerated. But also these slotted masses are also accelerating towards the ground. So we've got to take that into account as well. So the mass has to stay constant, and so if we change this force of weight, we actually have to do so by removing masses off this car and putting them down here on the masses. So I've gone ahead and taken the results off the from the video, and I've plotted them into a graph, and you can see that it forms a pretty perfect direct proportional relationship. As force increases, acceleration increases. Okay, the more you pull on something, the faster it will accelerate, which makes sense. How do we know it's directly proportional? Straight line through the origin. Okay, the origin down here. It's a straight line. It goes through the origin. Also, double the force. If you double the force, then you will also double the acceleration as well. So it's a directly proportional relationship. Force is directly proportional to acceleration. We have a constant in here, m, mass. Okay, so we kept mass constant. We didn't change it, as we said before. We took the masses off the car, put them on the hanger to keep the mass constant. And this is actually Newton's second law. This car obeyed Newton's second law. Okay, bigger force, bigger acceleration. Bigger force, yeah, bigger acceleration. In the second experiment, we did almost exactly the same thing, except this time we kept the weight the same. We kept the force constant. We kept F constant, and we changed M. So again, I've taken the results off the video. The mass, I've changed the mass. I've rounded it to two significant figures to match the rounding on acceleration as well. And again, we've got a graph. This time, it goes down. Okay, as mass gets bigger, acceleration goes down. Okay, acceleration gets smaller, as you'd expect. Okay, heavier things are harder to accelerate. The heavier something is, the harder it is to accelerate. Let's have another look at Newton's second law again. Force was made constant. Okay, so if we change the mass, in order for force to stay constant, we have to make acceleration change the opposite way. So if mass goes up, okay, acceleration has to go down in order for F to stay the same. yeah, and vice versa. If we make mass smaller, acceleration will get bigger. Lighter things accelerate more easily. Okay, so this whole demonstration, this whole practical was meant to demonstrate this Newton's second law here. F equals ma. Force is equal to mass times acceleration. Okay.